Welcome. Today we're going to talk about signed area and how to find it. So actually just estimating area in general, we'll talk about what signed area means, then how to find it using, today we'll just use left sums, but then we'll expand later to right sums, midpoint sums, and all sorts of things. And then an example. So, what do I mean by signed area? Well, we'll count the stuff above a graph as positive area and the stuff below the x-axis as negative area. I know area is positive no matter what. Whether it's up here or down there, it's area. But sometimes it's useful to talk about pluses and minuses. For example, suppose I drive 30 miles north and then 30 miles south. How far have I traveled? Well, in some sense, I've gone 60 miles. But in another useful sense, I've gone 0. I've changed where I am, 0. So being able to add pluses and minuses when we total things up is useful. And this is a way to do it. We're going to count this as the signed area from x equals a to x equals b under the graph y equals f of x. And you can see, if we're talking about under, that's positive, but under here, it's kind of flipped, so it's negative. And incidentally, if you ever want to do all positive area, so you want to count that as positive, what you could do is just put absolute values everywhere, and then it works fine. You may have seen this symbol before, hopefully, in a previous section. That was the indefinite integral. Now, because we have these here and here, this is called the definite integral. The definite integral from x equals a to x equals b of f of x dx. The dx is important. It's a part of this. It's like a bookend, they call it. But truthfully, it has a really important bit to it, and we'll talk about why it's there. But anyway, this is how you do it. We're going to look at ways to estimate using rectangles. So if you look here, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rectangles in here. And I've drawn them all based on a height equal to the function at the left side of that rectangle. So at the start, I've got one that's height is equal to f of a. Here it's f of, well actually it's 0. Here it's f of whatever that is. That determines the height. Why do I do this? Because if you look at the stuff I've got, the blues being positive, the reds being negative, it's almost the same as the function. It's not the same, because there's these bits off up here and down there. But it's almost the same. This way of estimating just makes rectangles. The area of the rectangles added together, plus or minus, makes about the same as the original function. Hopefully you can see, the more dense my rectangles, the better my estimate will be. Now, some details. So the left sums will notate L sub n, where n is the number of rectangles, n for number. And the height is equal to f at the endpoint of that particular one. And the width. Right now we're going to use the width is always the same. It actually doesn't have to be, but right now they're all the same. We'll call that width delta x. Now if they're all the same, if there are 10 of them here, then each one, the distance is going to be 1/10 of b minus a. If there are 7, it's going to be 1/7, and so on. So delta x is always going to be b minus a over n. So let's do an example of this, and then you can see how it is pretty close to what we're looking for, or at least it's reasonably close. So here's our example. We're going to try to find the definite integral from 1 to 4. Notice we start at the bottom number. It's 1 to 4. It's not 4 down to 1. It's 1 to 4 of x cubed dx. And we're going to do it using the sums L2 and L4. So I'll give you 2 seconds to try to figure it out. And then we'll do it. So L2. Well, in order to do this, we need the first rectangle, and then there's the second rectangle. 2 subintervals right here. So the left side determines the rectangle's height. There's one of them. Oh wait, 1, 2, 3. I drew all the way over to 2, and that's not halfway in between, is it? So, what is halfway in between? We want to make these equal widths. Well, if I'm going from 1 up to 1, 2, 3, 4. 4, halfway between there is 2.5. So the first rectangle goes there. The second rectangle starts here and goes there. Notice this is going to be underestimating the area. But what is this? So delta x here is going to be 4 minus 1 over 2 is 1.5. What is the area of that rectangle? It's width times height. So it's 1.5 times the height, which is the height on this side. Now what about the other one? Width times height. Same width. One of the nice things about this is it is the same width times height. So now what is the function? The function's right here. So this is 1.5 times 1 cubed plus 1.5 times 2.5 cubed. Now, maybe you could do that in your head. I'm going to get a calculator because I prefer just taking 2.5 cubed is 15.625. So what do I get total? Well, that's 1.5, and that's 23.4375. So ultimately, I get 24.9375. And as we said, just looking at that, it's an underestimate. Now, one way we can do better, let's try L4. So now I'm going to break it into 4 equal intervals. If I'm breaking it into 4 equal intervals, now each of these 2 intervals splits in half. Notice what happens. In general, when you add on a rectangle or make it more dense, you're going to get more accuracy. See, there's less missing. It's still an underestimate. In this case, though, delta x is going to still be 4. Delta x is going to be 4 minus 1 over 4 is 0.75. So that means the width times the height. How do you find this? It's going to be width times the height. And the first one starts in the same spot. We're only using left rectangles here. The next one is that far away. So instead of starting at 1, it's moving over 0.75. So it's f of 1.75. The next one moves over another 0.75, which we actually already knew. That's 2.5. It's the same place as before. And then the last one is 3.25 is how high, what the x is. 1, 2, 3, 4. Notice this last endpoint of 4 not being used because it's not the left part of any interval. It's the right part. Now, as a notice, if we started with all the right ones, what would have happened? We would have overestimated maybe about the same amount. So maybe, ultimately, we could do lefts, we could do rights, we can average. There's a whole bunch of things we can do. But let's finish this one off. Notice there's a 0.75 on all of these. Sometimes it's easier to put your delta x at the beginning. It's a lot of work, it's a lot of mess and number crunching. But if you do this, we got 1 cubed plus 1.75 cubed plus 2.5 cubed plus 3.25 cubed, all times 0.75. I get 42.234375. Let's keep 4 digits. There we go. It's bigger. Why is it bigger? Because we estimated more. If we wanted to only use lefts, could we get bigger still? Yeah, do 8, 12, 30, however many. At a certain point it gets tedious, but hopefully this shows you how to do it. Until next time, this is Dr. Jed.